Hi guys, so today I wanted to share with you two more problems from AtCoder, but today's episode is going to be a little bit different because we are going to use AtCoder library to solve these problems. You're not going to use something crazy out of it, but it is going to help us quite so. So the first problem comes from a recent ABC 216. It's problem G01 sequence. In this problem, we are given a sequence of lengths n consisting of zeros and ones that satisfies the following condition. We are given several segments from left eye to right eye, and the constraint is that there are at least xi occurrences of 1 in this segment. Like if we scroll down here and take a look at this sample, and take a look at these constraints. So we'll have a sequence of length 6 that satisfies 3 constraints. First, from first to fourth element, it has at least 3 ones, so exactly 3 ones in this case. Second constraint is from second to second, it has 1 occurrence of 1, that is also correct. And the last constraint is from 4 to 6, from fourth to sixth element, it has at least 2 ones. That's also satisfied. And among all such sequences of zeros and ones, we want to minimize the total number of ones. So I encourage you to think about this problem for some time, because it should draw strong parallels with the problem we had yesterday, also about segments, because in a way it's solved with a very similar technique. We want to process segments in some sorted order. It is going to be somewhat greedy, but the inner processing is a little bit complicated, and that's what we'll need AtCoder library for. So yeah, you can give it a try. That is not like not a very hard problem. There is a good chance that you will get some ideas after watching yesterday's video. So the way that we are going to solve this problem is the following. So let's take a look at our array that is initially, let's initially start with all zeros, right? Because by default, the elements are usually 0. We are going to consider each segment that we have a constraint. Let me actually draw them with the same color. And we have such constraint, we have such constraints. Maybe also a constraint somewhere here. Maybe also a constraint somewhere all the way over here. So the way I think it's reasonable to process such queries is like, let's once again go from left to right and think what happens. So far, just when we go over the opening, over the left endpoint of the segment, nothing actually happens. We just know that the segment started, but we don't have to do anything just yet. We may actually cross several left endpoints before we get to the right endpoints, and that's fine. It is not something you should be concerned about. What is tricky, what requires us to do some work, is when we cross the right endpoint. Because by the time we cross right endpoint, we should have at least xi ones in this segment. How to achieve this? How do we pick which xi positions inside this segment we want to fill? And the answer is we want to greedily fill the rightmost positions because it may be clearer if we take a look at these two segments. So this one is green, this one's red. When we reach the endpoint, the right endpoint of the green segment, let's say we want to put 3 ones into it. So we could do it somewhere over here, and then leave this to zeros. But it does not sound very efficient because these ones, they only help to satisfy the green segment. What we could do instead is start from the rightmost position and fill ones. So these ones will also help the red segment. And in general, like if you have multiple segments overlapping, like you already processed all segments that end before this point. So now all your segments, they look something like this. You have one segment that ends here, and all other segments, they look something like this. So the more ones you're able to place on the right, the better, because they get counted here, 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 basically everywhere. And you really don't want to place ones all the way on the left, because they don't get counted in any of the other segments. So what we will do is we will try to fill each segment, try to add as many ones as it needs, starting from the rightmost position. So that's like a plan. But if you think about it, like, first of all, we would like to know how many ones it needs, because we may have filled several ones already when processing segments that end before this segment. So we have several questions. First, how many we still need? How many ones we still need? And if you think about it, like we had our original estimate xi, and we added several segments, and let's have the difference. Let's say we added ai. So the difference is how many we still need. And if you think about ai, that is actually just a range sum from left eye to right eye. So you can already see that we'll need some data structure that supports range sum queries. And another thing it will obviously need to support, it will need to support placing down a1. So like range sum, so point update. That already sounds a lot like a Fenwick tree. But there is one more trick to this problem, and this is like, let me clear some of these segments to make a more general drawing. Let's say you had a segment like this, then you had this segment like this. Let's say this one needs like 2 and this one needs 4. So when you are processing this one, you said like, okay, this ends first. So we'll start with placing down 1 here, 1 here. Like what you may think like, okay, so this one needed 4 originally, and it got 2 placed, so it needs 2. So let's just go here and here, right, and assign 1. Well, no, because this position is already taken. So it's like taken. When you take a position, you should mark it as taken. And therefore, you should take the rightmost position, this first atmost right, and it's also not taken. You should use this instead. So for that, we'll need a helper data structure that is going to be just std set, containing all indices, all empty positions that are still free to fill. Like originally it's the entire segment, then we start, we can find the largest element that is at most right by using std set lower bound. That will give us a largest element up to some point, and then we'll have to remove that from the set. So yeah, hopefully the idea should be clear by now, because that is just sounds a lot like a problem we had yesterday. So yeah, let's take a look at the implementation now. And as I said, it makes use of AtCoder library, which is always like present on AtCoder. You can include it with include AtCoder all. And you probably want to use namespace AtCoder, because you don't really want to prefix all your fanfic tree names with AtCoder, with something like this, right? Namespace resolution operator. Probably don't want that, so this lines will be helpful, this one and this one. Now, when it comes to using AtCoder library, I believe the best resource is just GitHub for that. There is, well, first of all, there is the library itself that you can download or better clone the repo. Then add it to your like include path in whatever build system you're using. But if you're looking for the documentation, you should take a look at documents English. And it has like, it explains what actually the methods compute. Fanfic tree can update an element and calculate the sum. So not vice versa, just in case you're wondering about. The indexing is zero-based. And more importantly, the right endpoint is not included. So like int left, int right is a half-open interval, just in case. But you may accidentally pass it an empty interval if you say left is equal to right. That should also work. So yeah, that is the wrong submission. Let's get back. So you just got to be careful to make sure that you understand how the interface is working before you use it. So what we do in this problem, we just read our input. We use vector of tuples for that because we can conveniently read them like that. With a tuple in packing with reference. We can sort them by, generally we want to sort by right endpoint, but just a tiny pedantic feature. std sort, I believe, expects a total ordering, so and several of our segments may have the same right endpoint. In this case, I would like to break the ties whenever I can. So I break ties by left endpoint because I was told by the statement that there is never twice the same segment. And I also have a set of free positions. And normally std set lover bound returns the first element that is at least something. But here I want the largest element that is at most something, so I have to pass a std greater comparator here. So it starts with all elements being free. And I start with fanfic tree initialized everything to zero. Now you loop over my queries. Once again, tuple unpacking is your best friend in modern C++. You make sure to subtract however many ones you have already added to your fanfic tree in that segment. And as long as we still need to add some ones, I just take whatever free position I have that is as high as big as possible, but up to right inclusive. I make sure to add to my fanfic tree and remove the free position from the set. And you may think like, wait a second, that actually takes a long time because you loop over like every xi can be all the way up to n, and there are like m of them, so that's not cool. But keep in mind that the constraints of the problem, they told us that this assignment is always possible because xi is at most right eye, the length of I segment, let's put it this way. So what happens is because we subtract a lot of segment sums here, this operation can only happen n times overall because you always add into a free position and you have only n free positions. So overall complexity stays of n log n. Plus probably of m log m for sorting the m ranges. And to get the element from the fanfic tree, you have to use this syntax, sum from I to I plus first not inclusive. So it took me several tries to figure out the syntax, the semantics of like the half open interval before I finally decided to take a look on the GitHub. So yeah, like documentation is your best friend. Once again, there will be a link to the entire library down in the description if you want to use it. One nice thing, like it's always included on AtCoder. It's always present on AtCoder, so you can always include it. On other platforms, you would likely want to use expander.py. Expander. I'm not sure. Whatever, like you got the idea. I just make sure to copy paste the source code of something like AtCoder, fanvic3, to copy paste that into your submission, and also to recursively copy paste AtCoder internal type traits if you ever need that. So yeah, it's not large, but it contains a lot of helpful things that you may want to use if you don't have your own template, or if you like, for some reason, you mostly participate on contests on AtCoder and not so often on other platforms. You may find it very useful. I used it several times in contests and it helped. So yeah, like obviously I do have my fanvic3 template, but just like basically using library code cuts your own code in half, because you don't need to copy paste fanvic3. That may be quite nice. There are certain limitations to like what kind of algebraic structure fanvic3 supports. What I believe is a monoid. So yeah, just make sure that if you want to use it with some smart type instead of int, you may want to check the docs to make sure that it will work. So yeah. But this was a nice little problem. Hopefully you were able to figure out the general approach on your own. After yesterday's problem, that sounds quite likely to me. But we'll now take a look at the second problem that I wanted to share with you today, which is a string problem, somewhat unusual one. It's not the most common thing that you will see, but at the same time not something crazy. So, quite helpful approach generally, so that's why I wanted to share it with you. So we are given a string S. You want to form a subsequence basically with no two adjacent characters. And we are interested in counting how many different strings we can obtain. For example, from A, B, C, we can obtain A, B, C, A, C. We cannot take A, B because these are adjacent characters. On the other hand, from AA, picking first A and second A is identical, so we don't want to count this one twice. There are several more test cases that you can work your way through, but we are not going to do that right now. I would like to give you several minutes if you want to. You can pause the video and think about it, because it's a tricky problem. Like, it took me quite some time to figure out. Well, the general idea is not that tricky. Like, usually when you have a string from like lowercase English letters, quite often it means that you basically have to leverage the fact that there is a limited number of English lowercase letters, namely 26, which is like conveniently approximately the logarithm of what you're usually given. So that like something like alphabet size times length is a very common complexity in string-based problems. And this is what we'll have in this problem as well. So if we disregard just like if we disregard the fact that strings need to be distinct, and we just ask ourselves how many sequences, subsequences with no consecutive elements there are, non-empty by the way, we'll quickly understand that that's like approximately a Fibonacci number -1 for subtracting an empty subsequence or something like that, I believe. And it may give us an idea of using dynamic programming for our problem. Because like usually such things have to do something with dynamic programming. So what I originally tried is to like, well, I know that I am likely to get a complexity that has something to do with the alphabet size. So what I did was to, let me actually just make a normal table, because that one was a little bit sketchy. So my idea was to have a dynamic programming with the state being a position in our string. Like, let's compute answer for each prefix, all right? So for each prefix, we are interested in how many strings that satisfy the condition are up to this prefix of length I. But I also figured out that I kind of care what is the last letter. So I had dynamic programming that is like 26 times n. And I was trying to count like how many strings end in this position, or rather how many there are strings in this prefix that end with given letter. And then have like, but not necessarily they have this position, right? So that is just like, if that string is A, B, A, C, I would have like, I don't know, 1, 2, probably 2 strings. Let me just fill it. Like A, we have only 1 string, B and C we have 0 strings. Then here B is 1 string, we can't take A, B because that's consecutive. A remains 1, C remains 0. Here A is actually 2 because we can take AA. B still is 1, C remains 0. Now here C, we can take this one, and we can take this one, we can also take just C itself. That's like 3, then these two guys would stay the same. And then when considering this letter C, I was taking a look on this region, like column twice to the left. Now unfortunately that kind of does not work because I kind of tricked you. I said that I take a look at this column, but technically means that this A, it should have gotten A3, right? Because we tried to append in not 2, which would have been wrong, right? Because what like my general logic was, I take the current character, I also try all characters to the left, like skipping one column, and then I also take everything that ends with the same letter but before. So these two would be the same thing. The workaround, so that means that we are counting. Eventually we were just counting like how many subsequences with no consecutive elements there are, which is not great. So the way to get around this is to force your substrings to end at specific position. Because like the reason that we were getting several wrong answers, like overcounted, was that here we would count whatever ends here taking this letter, but we would also count whatever ends here taking this letter and skipping that letter, which is the same string. when you enforce a string to end at certain position, it means that when you look here, you will be appending A to strings that do have A already, so you will never consider this A and this A skipping that letter like twice. You will just append to strings that end at certain position. So that simplified things a lot, because what I know now is that I no longer have 26 by n dynamic programming, and instead I have just 1 by n dynamic programming, because I always know the last letter. When I'm in position I know that the last letter is SI, which may be something like, I don't know, D, right? So I always know the last letter. And the question becomes like, how do I compute it now? Because one naive thing would be to just go and try to append D to everything before, or rather skipping that location, right? To everything before, skipping that location. Now, unfortunately, that does not work, because once again, if we have several occurrences of A here, then this A contains this A, skipping that, and this A contains this A. So if we were to try to append D to both of them, that would end in duplication, like we count the same thing twice. So what it tells us, this A actually has this string as well. So why should we consider this A at all? Let's just consider the last occurrence of each character that we had, and it will have all the strings we need. So the idea we arrived at is the following. We will have dynamic programming that for each location I is going to tell us how many different strings with no consecutive elements there are ending at position I and containing position I. And our update consists of looking at last occurrence of each character, or skipping this position, and just adding that value here, because that's how many new strings we can form. And also technically we can start one new sequence with empty character, with like append D to empty string. It's like also +1. And in general, this idea is somewhat recurring. Like I remember problems that used this idea. Like you want to store the previous position of each element that you had. You want to try to append D to, so you basically have like DP over the previous character. That's why you're able to like, you loop over all possible previous characters. You knew you should take the last occurrence because it contains all other strings as well. So like this one, we are able to skip this A because this string is contained in the latter occurrence of A. Although it comes from different locations, it's still contained. So yeah, with that in mind, I believe we should be ready to take a look at the implementation, because it's reasonably short, and we make use of AtCoder library once again to take care of modular arithmetic for us, which is another nice feature it has. So like, you have a type modular integer in AtCoder library that you don't need to constantly mod in your program. So you only write it once, and you're able to use mint. Like just write vector mint and plus equals. You can see that I never mod DPI, it gets modded automatically. It's very nice. You can never forget about modding anything. And you also don't need to store long integers. Like your memory usage is lower because you don't need to use long integers. Well, you technically don't need to use long integers even if you mod yourself. You can just kind of multiply by one long in between and then mod the result. but that's kind of annoying to remember always when you want to multiply by long and when you want to mod. It's much simpler to just use AtCoder library for that. Or have your own model or integer template, but that's kind of a thing that's not that many people have, I believe. Then this problem will record previous position of each character, but I actually lied to you a little bit, because I said that we skip the previous position, as you can see here and here. And because of that, we actually need to store two last occurrences of each character. Because if we skip the last one, which was I, then we still want to consider what happens if that was the previous character. We just can't take the last occurrence, we take the second last occurrence. And it's guaranteed to be valid because, well, we only skip one position. So remember +1, we can actually do it at the very beginning. So there is one subsequence ending at each character, that is just this character, and the longer ones will add in this cycle, in this for loop. So we loop our all positions, we loop our all previous characters. By default, we try position A, which is the last position of this character. It's initialized to -1, so that if this character has not appeared previously, then we'll just skip both of these loops, ifs, and do nothing, which is reasonable. Like, you can't have a subsequence with previous characters that has not appeared previously. So by default, we try the last position. If it unfortunately is just I, then we skip it and we take the second last position. This condition can never be true, I just have it for kind of symmetry here. In case you're wondering why this is here, you can remove it. And just increase, we consider all strings that end with this character, and we append our current character to them, which corresponds to adding all these options here. And once again, the modding operation gets done automatically because that's not int, that's mint, modular integer. And also we need to update last position, which we do with this tuple syntax or pair syntax. And once again, with computations of answer, we just consider whatever was the last character of our string or subsequence, and we add all strings that end with this character. We can't just take the last element, because last element enforces you to take the last character, which you don't necessarily want to do. So that's why this for loop is also necessary. And once again, it's nice to check that you actually had this character in your string by checking that last position is non-negative. One little thing but using AtCoder library, because mint is a class of some sort, it's very lightweight, but to get the actual value, to print it, you need to call a method. It's a little inconvenient, but it is what it is. There is no operator overloading for it. Not exactly sure why this happens. I believe you should, if you are really interested why you need to call value, why you can't just print. I believe it's because, well, like, if you just overload the operator, the shift into the stream, it's not going to help people who use printf syntax. So like you need some sort of way to get the actual string out of it, or integer. So meaning that that method would be necessary regardless, even if you have overload. So they just decided to like leave it the way it is. So yeah. And this approach with storing last occurrence of each character, I believe it occurs in several interview problems as well. But like the very harder ones, I have not seen it like in easy problems. That is definitely not an easy interview problem. That is something much closer to competitive things. So yeah, that's what I wanted to share with you today, and tomorrow we'll be back to code forces, solving some master level problems already. Finally, some of you requested to get into other harder problems, because apparently such problems as we have on Monday, Tuesday, Wednesday, they are a little bit trivial. So yeah, don't you worry, we'll be the difficulty will escalate quite quickly. Yeah, and I'm almost done with upsolving the contest from the previous weekend. What I may do is something that's not going to be very popular as a YouTube content, but next Saturday I will make an analysis of all contests that I participated in previous week. So obviously the delay is quite long, but maybe that is actually nice. If some people wanted to upsolve contests during the week, they had a chance, and now we can do our analysis. Like after people had chance to upsolve, probably they did not upsolve everything, because I myself did not upsolve everything just yet. I still have problem H from ABC remaining. So yeah, maybe that will actually be good. I don't know. I think like I'll go over all hackers, AtCoder, and code forces. Maybe I will even include this code forces coming up today in that analysis, because doing screencasts is not very good for performance. Like you do a lot of commentary and you may get carried away from actually solving problems. Fortunately, that happens to me sometimes. So I believe I'll switch to like post-contest analysis format. It's hard to make them like on a daily basis. So maybe that was something that will happen once a week. So yeah, and on the other hand, it will contain like analysis of several contests. That's like more content for you. So yeah, I hope you like enjoyed this episode and learned something new. And I encourage you to always try to solve our problems before you see the solution. Or at least like, well, maybe you already tried solving it and you could not solve it, and that's why you are coming for this daily show. Then try to implement the solution after the video. Because of course watching videos is easy, but like actually solving something is a little bit harder. But if you really want to progress yourself, then you should be writing code yourself, right? So yeah. So good luck with that, and I'll see you tomorrow, guys. Bye bye.